Welcome to our 7th lesson on electromagnetism. We'll be taking a look at transformers today. Now I'm sure you might have heard about transformers before, but this type of transformers that we're going to be taking a look at is specific electrical devices that will in this case either step up or step down my potential difference. That means increases or decreases in it. Now our transformer is basically made up of an iron core. And you would note though that it's a metal shape in this specific form. Now we will be calling the one side of this iron core the primary coil and the other the secondary coil. Now it's basically based on electromagnetic induction, but moreover mutual electromagnetic induction, which means that we will be having on the one side a current and a magnetic field, or a current and a force that will induce a magnetic field on the other side, and that together with our magnetic force will then again induce current. So we'll be starting off here on my primary side with coils wounded up around this iron core. Now these coils must be connected to an alternating power source, because we would need a constant change in the direction of my current in order to induce a magnetic field. So if we do have our alternating source as is, then we'll note that our current will flow in one direction and then suddenly swap around flowing in a different direction. And every time that it changes, in this case the direction of the current, it will induce a magnetic field. But it will only induce a magnetic field if there is a change in current. That's how come it must be an AC source. If we have a DC source, that means a direct current with a fixed positive and negative that is now wounded around this coil, our problem would be that our current will only run from positive to negative, and that will induce one magnetic field that will then stop after a few seconds. But if I've got an alternating source, then it will constantly, every time that this current is changing direction, induce a new magnetic field. Now the reason for us wanting a magnetic field induced every time is that so that this magnetic field can travel through my iron core, that is magnetic, to my secondary side. Now this secondary side will also have a number of loops, wires surrounding it. And this could now be connected to something like a bulb. Note though that this loop or wires is not connected to any power source. But because of this induced magnetic field that's constantly going to change direction, because the current changes direction, there will now be a current induced in these secondary wires. And that current will then make the bulb glow. So this is the basis on which transformers is then functioning. So we'll have a changing current on the primary side that induces a changing magnetic field that on the other side will induce a current again. Now we're going to be taking a look at what we call step up and step down transformers. Now our step up transformers will take a low potential difference or induced EMF to a higher potential difference or induced EMF. Remember, PD is the abbreviation for potential difference. And what it would need in order to do that is a low number of windings on the primary coil. Now remember, number of windings will be indicated by a capital letter N, and the P subscript will stand for the fact that this is what is noted on the primary part of the coil. And that will then take it to a high number of our number of windings on the secondary coil. So in order to make sure that you've got a step-up transformer, which means you want to take your potential difference from a low value to a high value, you would need to go and place less windings on your primary coil and more windings on your secondary coil. So we'll change the number of windings in order to go and change the potential difference. And step up meaning that it's going to go to a bigger value. Now let's go and take a look at your step-down transformer. Here you want to go from a high potential difference to a low potential difference. And just like in the case with my step-up transformer, you're going to need to take a look at your number of windings. If we want to make it a high to a low potential difference, then we would need to make sure that we've got a high number of my windings on the primary coil, and then when we take a look at my secondary coil, there must be a low number of windings on the secondary coil. So that's the changes that we would make in order so that we end up with a lower potential difference. What is important to take note of though, is if we go from a low potential difference to a high potential difference, your current will do the opposite. That means if I do a step-up transformer, I'll go from a high current to a low current. So remember, it's always the opposite of the potential difference. The same applies for my step-down transformer. That means instead of going from a high potential difference to low potential difference, I'll go now from a low current to a high current. Now when transporting our electrical energy across my power cables, you would note that in our country, we are then generating our electricity at one point, and then from there, before we're going to let it be transported across these overhead power cables, we are going to be making use of a step-up transformer. Now step-up means that we'll be transporting this electrical energy at a high potential difference, but the opposite for my current, which means a low current. On the other hand, the moment that we do end up again at our substations, when it goes to our homes, then they're going to be using a step-down transformer. And that means it's going to have a low potential difference, but a high current. Now we do want to make sure that this electrical energy gets stepped up so that we transport our electrical energy at a low current. A high current will lead to a lot of my electrical energy being converted into heat energy. And that means that we will end up losing electricity basically. So therefore we're going to be making use of a low current within my power cables so that there will be less energy that will be transferred to heat energy, and thus at the end of the day, less of my electrical energy lost. Now we're going to be looking at two formulas in which we can make use of to calculate the potential difference or the number of windings on the primary and secondary coil. The first one is making use of our potential difference across S. Now please note S stands for your secondary coil, divided by the potential difference of your primary coil. And that's equal to the number of windings on the secondary coil divided by the number of windings on the primary coil. Do take note though that number of windings do not have a unit because it's just indicating a number of. Our second formula would be making use of my potential difference in current. Here my potential difference on the primary coil times the current on the primary coil would be equal to the potential difference on the secondary coil times the current on the secondary coil. Now let's first go and take a look at an example of these type of calculations. A step-up transformer is used to convert a potential difference of 200 volts to 500 volts. If there are 30 turnings on the primary coil, how many turnings would there be on the secondary coil? Now seeing that we're talking about potential difference and number of turnings, we'll be making use of our V and N formula. Now we have been told that we want a step-up transformer that goes from 200 to 500. So initially in the primary starts at being 200 and then it wants to go to 500, which will be its part in the secondary. And they tell us that your primary has got 30 turnings on it. You need to go and determine what will be the number of turns on the secondary coil. So in order to do so, we'll just multiply out with our 30. And that gives me a total number of turnings of 75 on my secondary coil.